Hello everyone, welcome back. Can you hear me? I'm missing something. Hello everyone. Hi Raghav. Good to see you back. Awesome. Awesome. Hi Vimal. Awesome. Can everyone hear me? Awesome. All right. So I'll get started in one more minute, in a couple of minutes, just to wait for a few people. Hi Hardik Pandey. Nice name. Nice name. Awesome. All right. So in this I'll be hello, yeah. Just give me a minute. I'm just setting up a few things here. Just give me a minute. Just give me a minute. All right. All right. Awesome. So, good morning, everyone. Welcome back. I'm Sai Avinash, and in this lecture series, the I'll be solving problems live, Codeforces problems live. I'd be picking problems that are just like at or above your threshold. That's what I'd be trying. Something around the range of 1400 to 1500 or 1600. In the last ad hoc series, last ad hoc class, for example, I initially start my class with an easy problem and then go pick another harder problem. So in the last class, I think I picked something like the first problem was 1100 and then the other problem was 1600. So just so that you improve as you watch this series, and of course, this alone is not sufficient at all. You need to solve problems on your own as well. Anyway, a little about me before I start the class. I'm a software. I'm an SRE SWE at Google Dublin. All near rank 4 at CodeChef. I'm a 7-star coder there. I'm Max International Master at Codeforces, and currently a master there. Previously interned at Uber, and I'm also a Snackdown finalist. The subjects that I take are discrete maths, dynamic programming, graphs, and a lot of other competitive programming topics. Use the code SciLife to get a 10% off on the Unacademy Plus subscription. So don't forget to join the Telegram channel. to get live updates on the latest process, so that you don't miss out on any of them. Raghav asks, do you have any recommendations from where to subscribe practice ad hoc problems? I think AtCoder has a good collection of ad hoc problems. Yes, atcoder.jp. That's a really good site. It has a good, it has a nice collection of ad hoc problems. So you can check out the beginner contests or regular contests, or the first problems of grand contests. Yeah. Regular contests, AtCoder regular contests are like usually good. Yeah. Anyway, so if you think this content is going to be useful to you, drop a like and share it with your friends if you think it's going to be useful to them. And if you don't want to miss out on any such videos in the future, do subscribe to this class. Do subscribe to this channel here. So let's solve problems. Again, as I said, I'll start off with an easy problem first. It's a 1400 rated problem. Let me copy paste the link here. So this is the question. I'm just pasting the link here. Yeah, beginner contests are also good. Like AtCoder contests in general are pretty good. So anyway, let's get started. So composite coloring. A positive integer is called composite if it can be represented as a product of two positive integers, both greater than 1. Example, the following numbers are composite: 6, 4, 1, 20, 27. 1, 2, 3, 17, 97 aren't, because they're prime numbers. Like, okay, sorry, that's the wrong definition. Anyway, 1, 2, 3, they don't have a, they can't be represented as a product of two positive numbers, both greater than 1. Now, we're given a sequence of n composite numbers. She wants to choose an integer m less than or equal to 11 and color each element one of m colors from 1 to m, so that for each color from 1 to m, there's at least one element of this color. So you need to color each number from like each of these numbers, a color from the range 1 to m. You need to pick an m, and then you need to color each of the elements from 1 to m. One of these, each number should be colored, any number from 1 to m, such that like each element is exactly colored with one color, and each color is used exactly at least once, and the greatest common divisor of any two elements that are colored the same color is greater than 1. Meaning, like basically you're putting all the numbers into like m buckets, where each bucket represents a color. Like the numbers that are colored 1 are put into bucket number 1. Numbers that are colored 2 are put into bucket number 2, and so on. Now in each bucket, if you pick any two elements, the greatest common divisor should be greater than 1. Is that clear? What the question asks is, you're given n numbers, you need to put them into m buckets, and m should be less than or equal to 11. That's the most important condition. Otherwise, you could just make n buckets and put each element over there, right, in its own bucket. Anyway, let's get into that later. Let's understand the question first. Now, you need to put each element in a single bucket. There are m buckets, and towards the end, once you look at the bucket, like each bucket has a bunch of elements, right? Maybe A1, A3, A4, or something like that. Bunch of elements in each bucket. Now, in each bucket, if you pick any two elements, they should have a GCD greater than or equal to 1. That are colored in the same color, meaning are present in the same bucket. The GCD should be greater than or equal to 1. Greatest common divisor of any two elements that are colored the same color should be greater than 1. Meaning GCD of AI, AJ should be greater than 1. What are the constraints that we have? Note that equal elements can be colored different colors. Okay. You just have to choose one of m colors for each of the, like you just need to choose for each of the elements from 1 to n. You need to choose a color basically. Now, if AI is less than or equal to 1000, turns out that you can always do by choosing m less than or equal to 11. How? We will figure it out. Now we just need to find the required coloring. Note that you don't have to minimize or maximize the number of colors. You just have to find the solution for some m. Okay, I'll explain the question. No worries. I shall explain the question. Let me clear this off. So what does the question ask? What does the question ask? You're given n composite numbers. That's one of the key parts of the question. You'll understand why. N composite numbers. A1, A2, A3, so on till AN. Note that they're composite numbers. For example, you won't get, the input will never be 3, 10, 12, 2, for example, because 3 and 2 are not composite numbers. They can be, for example, 6, 10, 15. Now you can, the question says you need to pick an M and then you need to just put them in M buckets. You need to color them in one of M colors basically. So note that, okay, for example, in this, we can pick 2 buckets. For example, in the first bucket, you can put 6, 10. For example, or like, I'll just speak in terms of colors, you can M equals 2. There's a solution for this. For example, you can put this and this in, you can color this and this as A, or okay, 1 to M, right? Basically 1, and you can color this as 2. Basically, you're putting in one bucket, you're putting 6, 10. In the other bucket, you're putting 15. 6 and 10 have a GCD greater than 1. GCD of 6 and 10 is 2, right? That works well. All right. Now, we can do it in 3 buckets as well. M equals 3. Of course, we can do it in 3 buckets because 6, 10, 15. Like for a given n, we can do it in n buckets. Each element can belong to its own bucket. That's a solution because GCD of the element with itself is basically GCD of 6, 6 is 6, right? So GCD of the number itself is always going to be greater than 1 because a composite number is going to be greater than 1. For example, GCD of A, A is greater than 1 for A is composite, right? Anyway, for example, if you're given 10, 42, 70, 33, you can always put them in 4 buckets. 33, M can be equal to 4 here. 10, 42, 70. But n is up to 1000. And wait, where is n up to? Yeah, n is up to 1000. N can be up to 1000. So in that case, you can't have 1000 buckets. You need to be smart. You need to like reduce the number of buckets. You can't always have indefinite number of buckets. We have the constraint where m is up to 11, right? M is up to 11. You have this constraint, right? So what do we do about that constraint now? What do we do about that constraint? All right, let's look at it. So say we have the numbers 10, 12, 7. No, 7 cannot come. 27 can come because it's a composite. 42, 35, 8. Now, of course, let's try to minimize, like, let's try to reduce the number of buckets. Not minimize, let's try to reduce the number of buckets. So what do you mean, like, what do you mean when all numbers are there in a bucket? For example, that it means that any 2 numbers will have a common factor, or more specific, common prime factor, right? Which is greater than 1, of course. Yep. Yes, we just need to group them into disjoint sets. For example, you can group 8. For example, one option is to group all even numbers here. 8, 10, 12, 42. And in the other group you can put 27. You can see that 35 doesn't really go with any of them. Like, because 35 would have gone with 42. 42 can come here, or it can come here as well. But anyway, we group them into 3 sets instead of grouping them into 7. All right. So how do we solve this problem? And more importantly, we are given that AI is less than or equal to 1000. 1 less than or equal to AI less than or equal to 1000, but AI is a prime number, so I mean it starts from 4 essentially. Anyway, AI can't be a prime number. AI should be a composite number. All right. Now how do you find 11 buckets? Where does this number 11 come from? All right. One crucial observation is, if AI is composite, if AI is composite and AI is less than or equal to 1000, which means AI can be written as P into Q. So when we write P into Q, it means that, let's assume without laws of generality that P is less than or equal to Q, which means that P should be less than or equal to root AI, right? When you're writing AI is equal to P into Q, one of the numbers has to be less than or equal to root AI. Because if both are greater than root AI, it means that P into Q will be greater than AI. For example, you have two numbers, you're multiplying them and you're equal to X. Let's call it Y. Both are greater than 0 and Y is also greater than 0. One number has to be less than root Y and one number has to less than or equal to root Y, and the other number has to be greater than or equal to root Y. Because if both are greater than or equal to root Y, one sec. Just give me a minute. Yeah. Because if both are greater than root Y, root Y, for example, if 25, for example, Y is equal to 25. If both are greater than 5, it means that this product would be greater than 25. So the smaller number of these two will be less than or equal to root Y. Okay, similarly, the smaller number of these two, let's call that P, for example, is going to be less than or equal to root AI. And we know that AI is up to 1000, which meaning the smaller factor of AI, P is the smaller factor of AI, it's going to be less than or equal to root of 1000, which means P is going to be less than or equal to 31. It's 31 point something, 31.6 or something, but let's not go there. Less than or equal to 31 is it's a thing. 31. So the smaller number of the smaller prime factor, the smaller factor for that matter, so it's going to be less than or equal to 31. And we are always going to have a factor less than or equal to 31 because AI can be written as P into Q, where P is not equal to 1. It can always be written as that. Once it can be written as that, we found that P should be less than or equal to 31. Is it clear so far? So far, is it clear? Is this clear? Any doubts with this so far? Any doubts with this? Any doubts with this so far? Any doubts with this? Awesome. Okay. All right. Now what we do is, now since the smaller factor is less than or equal to 31, it means that there's a prime factor also less than or equal to 31. The smaller factor is less than or equal to 31, which means there is a prime factor which is also less than or equal to 31, right? So we can say that the smallest prime factor of AI, is less than or equal to 31. Correct? Hiron is asking for every number from 2 to root 1000 and check if it's any fact. Okay, so Hiron asking like we could put all the numbers from 2 to root 1000, which is basically 31, and we know that each of these numbers has to be a factor of some AI, and put it in that bucket. But you might have more buckets than 11, right? That's an issue. All right, the smallest prime factor of AI. Before that, let's look at one more thing. Let's go in the direction that Hiron suggested. So we know that each number from 1 to A1, A2, A3, so on to AN, each of these numbers has a factor from 2 to 31. Has a factor from 2 to 31. Right? How many numbers are there from 2 to 31? 30 numbers are there. Okay. Now we can make 30 buckets. We can always make 30 buckets. We are reaching an improvement here. We can make 30 buckets where each number falls into the bucket of its smallest prime factor. For example, if you have 102, this is essentially 2 into 51. So 102 falls into the first bucket, which is 2. The second bucket is 3. Third bucket is 4. So on. We'll come to an improvement, a small improvement, and then we'll get the answer. Like this is great improvement, right? We do it in 30 buckets. So we group each. If A2 is say 17 into 13 to 21. 221 is 17 into 13. So we put it in the bucket named 13 because 13 is the smallest prime factor, 221. Similarly, say we have 13 into 11 or like 13 into say 19, which is 249. I'm sorry, what's 13 into 19? 13 into 19, 247, right? 247. So we have 247. So 247, the smallest prime factor of the smallest factor of 237 is 13, right? So we put 247 into 13, the bucket name 13 as well. So in the end, in each bucket, we're going to have a lot of numbers which have the same common factor. 2, for example, in this bucket we have 3. All the numbers whose smallest factor is 3. In this we have all the numbers whose smallest factor is 4. Essentially, this bucket will never be full. It'll always be empty. Like all the numbers that are not primes will always be empty, because if a number is multiple of a non-prime, it means that it's a multiple of a prime that is lower than that number, right? For example, if a number is a multiple of 4, it's always a multiple of 2. So it will go here instead of here, right? Okay. So essentially for each number, anyway, so once you filled with these buckets, we do have a solution, but for m equals about 30, we have a solution. Right, for m equals 30, we have a solution, meaning for m equals 30, we have a solution. For each bucket, for each number, we put the number, we find the smallest prime factor, and then smallest factor, but you can see that the smallest factor is the same as the smallest prime factor. It's the same thing. Anyway, smallest factor, and that's going to be less than 31. So we can put it in that bucket. So we have 30 buckets in total, but we want up to 11 buckets. If you look at it closely, we can see that only 11 buckets are going to be filled. I'll tell you why. At most 11 buckets are going to be filled if you do this way. I'll tell you why. Because all the buckets whose name is composite numbers, the buckets whose label is composite numbers are going to be empty. But let's look at how many prime numbers are there from 1 to 31. 2, 3, 5, 7, 11, 13, 17, 23, 29, 31. How many are there? 4, 4, 2. There are only 10 prime numbers. Right. So for each number, you can find the smallest prime factor. Even if you did it in the last way, you'll still have the same buckets filled, because as I mentioned, the smallest factor of a number that is greater than 1 is same as saying what is the smallest prime factor of that number. Because the smallest factor greater than 1 cannot be a composite number, because the composite number can be further divided into a smaller prime number, and that will be a smallest prime factor. Anyway, So once you're given an AI, you put it in this bucket. Put it in the smallest prime factor. For example, you have 35, 210, 147, 221, 246, 247, and so on. So 35, you put it in the bucket label. This is 5 into 7. So you put it in the bucket label 5, 35. 210, you put it in the bucket label 2. 147, you put it in the bucket label, this is 3 into 49, right? So you put it in the bucket label 3. 221, put it in the bucket label 13. 247, you put it in the bucket label 20, because this is 13 into 19, 13 into 17. So you can see that these two numbers have a common divisor, which is 26, which is 13, sorry. Right, 13 into 17, 13 into 19, and so on. Say you have 85. 5 into 17, you put this here, and so on. 35 and 85 always have a common factor, right? And we can always say that there are at most 10 buckets. 10 buckets, right? At most 10 buckets. So we're done, right? So given a number, we simply put it into the bucket with the, what do you mean, or what do you say? The largest, so the smallest prime factor, and that smallest prime factor is going to be less than 31 because of how the question is asked. Is this clear? Any doubts with the solution? Any doubts with the solution? Is there anything you want me to re-explain? Clear? Is this clear? Any doubts with this? Any doubts with this solution? Any doubts? If there's any part of this which is unclear, please let me know. So how did we go about this problem? So first we had n integers, a1 to an, and now for each number, you wanted to put them in a bucket in such a way that every number in that bucket, every pair of numbers in that bucket has a GCD greater than 1. So one way to group them is by prime factors. Like we just found out that like the smallest factor of that number is going to be from 1 to 31, right? 1 to 31. Once it's from 1 to 31, we found out that the number of prime factors is just 11, just 10. From 1 to 31 is just 10. And now each number from 1 to 1000, each composite number from 1 to 1000 is going to have a prime factor from 1 to 31, whose prime factor is from 1 to 31, which is essentially these numbers, right? Essentially these numbers. After that, we figured we can just group them into those prime factors. Like we can label this prime factor as 2, we can label this prime factor as 3, and so on. We can put a number into the bucket it belongs to, and then we'll have at most 10 buckets. 11 is a little slightly loose bound. We can do it in 10 as well. I guess the intended solution was to put 10 as well. They just put 11 for some illusory, I think. I don't know why. So let's get to coding. Awesome. The problem is, I'll send you the link of the problem. 1332b. And my name is Sai Avinash, so you don't have to call me by CodeBeyond. So essentially the number is, you need to group a bunch of numbers into like buckets, and so that in each bucket no two numbers have a GCD equal to 1. That's the TLDR of the question. Awesome. So we have test cases. Awesome. So we can just like hard code the primes. All right. Oh, I missed 19 here, by the way. There are actually 11 primes still. 11 primes. Got it? So m equals 11 is a strict bound. Anyway, or you can just try to generate those primes as well. Anything works. I'm taking the test cases first. Solve. Now, void solve int n cin n. Now vector buckets of int m equals, for example, buckets. How many buckets do I want? Basically the size of primes. 11 buckets I want. 11 buckets. Primes dot size. Now, for int I equals 0, I less than n, I plus plus, int x, cin x. Now I want to see where x goes to. So int p primes, if x modulo p equals 0, break, or rather int I equals int j equals 0, j less than primes dot size, j plus plus. If x modulo primes of j equals 0, then I just put it in that bucket, dot push back, I break. Now what do I have to do next? All right, till here, is it clear till here? So for each of these special primes, what am I doing here? Or like, you know what, I'll actually generate them instead of it seems wrong to actually hardcode them. So I equals 1, I less than equal to 31, I plus plus, if I modulo j equals 0, I'm generating them. It felt wrong to actually hardcode them. So bool prime. If is prime, primes dot push back, I. That's it. Anyway, now is this clear so far? Like, I first primes contains all the primes. Now after this, you're creating since we're creating 11 buckets essentially. The number of primes under 31 is 11. This is just me checking if it's a prime or not, and so on. Hope I didn't make a mistake here. Yeah, I didn't make a mistake. Yeah. Anyway, so this is essentially checking if a number is a prime or not. After this, once I have those primes, For each number, this is basically AI. I didn't take in the input because it wasn't necessary. I check each of these primes, each of these special primes. If it is divisible by AI, I'll just call it AI. If AI is a multiple of primes of J, then I put I into the bucket of J. Jth bucket. If AI is divisible by the jth prime, then I put I in the jth bucket. As simple as that. Right. Vector int bucket number of n. Note that I need this because the output format is such, meaning is everyone following me? Does anyone have any doubts so far? Like, does anyone have any doubts till here? Does anyone have any doubts? I don't want to skip things. Is it clear so far? Are you guys following me so far? Awesome. Awesome. All right. Now we have a few more technicalities that we need to take care. We almost have the solution. We just need to like code it properly. So we need to print two lines. The first line should contain the integer m, the number of buckets, the number of used colors. Consider colors to be numbered from 1 to m. The second line should contain any coloring that satisfies the above condition. Print n integers c1 to cn, where ci is the color of the ith element, meaning for the ith element, what is the bucket number? If there are multiple solutions, you can print any of them. Note that you don't have to minimize or maximize the number of colors. You just have to find the solution. You don't have to minimize anything or maximize anything. Okay. Remember that for each color 1 to m, okay, so each color should be used exactly once, meaning we need to discard the empty buckets. So let's name the buckets. Let's rename the buckets. In bucket number. First bucket number in current bucket equals 0. For int, the buckets start from 1, right? Yeah, a number from 1 to n. So I'll write current bucket equals 1. For int I equals 0, I less than buckets dot size I plus plus. If buckets is empty, buckets of I is empty, continue. Otherwise, for int j, like for int, what do you say, nums, num in, for each of these bucket, each of the numbers in this bucket, we name this bucket number of e equals current bucket, then current bucket plus plus. By this, we are making sure that this is the current bucket number. We are incrementing it each time. Now, for int I equals 0, I less than n, I plus plus, cr current bucket number. And how many buckets are there? It's essentially current bucket minus 1, because in the end you are incrementing by 1, right? CRN. Is this clear? Is it clear what I've done so far? Do you want me to re-explain this? What I've done here is I'm keeping the since I really want to satisfy this condition, right? Remember that each color from one term should be used at least once. Like if I directly print the bucket number, it means that there can be some buckets which are not used. but the output format doesn't support that. Like you want the output to, like you want each bucket to be filled exactly once. So whenever a bucket is empty, I skip it. If it is not empty, then I mark all the elements in the bucket to be current bucket. Now once I'm done with this bucket, I'm incrementing the current bucket by 1. This is to make sure, like for example, say I have like multiple buckets like this. In my first bucket, this bucket is for prime number 2. This bucket is for prime number 11. So I'll just put it like this. 2, 3, 5, 7, 11. And say that I have a bunch of numbers here, 42, 26, so on. 14 and 26. Here I have 39, 40, 39, 51. Here I have 25, 35. Here I have 49. But say 5 is actually empty. Say you have 49 here. For 11 you have 121 and 143. Okay, all right. Now we can't just print 5, say that there are 5 buckets. No, we need to tell that there are 4 buckets and label all these numbers. All of these are in the first bucket, all of these are in the second bucket. We shouldn't say all of these are in the fourth bucket. We should say that these are in the third bucket. All these are in the fourth bucket. We need to skip this bucket because empty buckets are not allowed. Empty buckets aren't allowed, right? Empty buckets aren't allowed. This is clear. So what we are doing here is, this contains what all is there in this bucket. What are the numbers that are there in this bucket? Now, once we encounter an empty bucket, so once we encounter an empty bucket, we skip this bucket. So we mark this 1, we mark this 2. We have this bucket, so current bucket will still remain 2 here because we're breaking it here. And then once we break it here, we go here, we make this 3. Once this is done, we make this 4. And since we need to print the bucket number of each element, we print that towards the end. This is clear. Any doubts? Any doubts with the solution so far? Is there anything you want me to re-explain? Any part of this confusing or any part which is like, okay, this is magic, I didn't understand this. I'd be happy to re-explain this. Any doubts with the solution so far? Got it? Awesome. Now, yes, so the main idea is you just need to, the buckets, you just need to deal with exactly the prime numbers from 0 to 31. You don't need anything more. Got it? I actually wanted to finish another problem today, but I guess we're out of time. Got it? Anyway, I can just give you a few modifications of this problem itself. Like if all the numbers were like up to 10 power 5, then it would simply be the number of prime numbers less than 10 power 5. We can put that in that many buckets. You can probably do better, but yeah, I don't know if you can do better or not. All the prime numbers less than or equal to 10 power 5, root of 10 power 5, less than or equal to max value in general. You can always do it in these many buckets. Is that clear? Awesome. All right. Are there any other doubts that you want me to explain, or is there any problem that you want me to explain now? Are there any doubts? I hope I made this clear. So I'll just so for those who just came, I will just give them a quick summary. Looks like a few people came just now. Anyway, so the question was, you're given a sequence of n composite numbers. Now you want to choose like m. You want to put in those numbers into m buckets. You're given n composite numbers. You want to put all these numbers into m buckets, and at most 11 buckets. At most 11 buckets, so that each number belongs to exactly one bucket. And once you're done with putting all these numbers into a bucket, when you look at each bucket, any pairwise GCD of any two numbers should be at least it should be greater than 1. It should be greater than 1. And the most important condition is AI is up to 10. AI is up to 1000, and all the numbers are composite numbers. Did you see that? All the numbers are composite numbers. That is where we pick our observation, because if there weren't composite numbers, if this condition wasn't there, then there was no way we could have put it into m buckets. We could have put it into 11 buckets, because all these n numbers can be primes, and all of them will have to be in different buckets, because if any two prime numbers are in the same bucket, any two different prime numbers are in the same bucket, then the GCD will become 1 and will violate the condition. So them being composite numbers was a crucial thing here. Himanshu, I have no idea. I don't even know who that person is. So anyway, for each, so composite numbers was a crucial thing here. And additionally 1000 and 11 have a strange relation, meaning the number of prime numbers less than root 1000 is 11. That's how they're related. Got it? And okay. What did we do here? N composite numbers, each one is up to 1000, right? Each one is up to 1000. So what we did was, each one is up to 1000. So what we did was, we figured that if a number is composite, and if a number is composite, it can be written as p into q, where both are greater than 1. I mean, it's then the question itself. So now that it can be written as p into q, like x is equal to p into q, the smaller of p and q will be at most root of x, because when you multiply two numbers and get a resulting number, and all the numbers are positive, one of the numbers is going to be less than or equal to root x, root of the product, right? Because if both are greater than the root of the product, it means that both are greater than the root of the product means that the product would be greater than product. I mean, you get a contradiction essentially. Anyway, so we found that the smallest factor is going to be less than root 1000, which means the smallest prime factor is going to be less than root 1000. When I speak of smallest factor, I exclude 1. The smallest non-trivial factor is greater than 1 and less than root of 1000. So once we found that all the prime factors are from 2 to 31, one of the prime factor from 2 to 31 is going to be a factor of this number, of this, what do you say, composite number, which is up to 1000. Himanshu, please stop spamming. I don't know who that person is, so you just need to stop spamming. And once, okay, anyway, now we need now essentially we need to put them into buckets. We need a way to put them into buckets. So once we put them into buckets and we find that no two numbers in the same bucket have the GCD equal to 1, we're done. So we found that we can group them into prime factors, the smallest prime factors, because all the prime factors are, all the smallest prime factors are going to be between 2 and 31. And the number of prime factors from 2 to 31 comes from root 1000, right? So 2 to 31 is just 11. And we can just put them into those buckets and we are done. Is that clear? Is that clear? I don't know why you guys are spamming, just don't. Anyway, are there any more questions here? And that's what we did. We put them into, we first calculated what the primes are, we put them into the primes. And once we put them into the primes, we just, what do you say? We put them into those buckets. You put them into those buckets, and once you compute those buckets according to those smallest primes, basically from this you get the smallest prime, and this has to happen. This has to happen. Always will. Because AI is prime. It's composite. And less than or equal to 1000. Got it? And once this is done, we have a bunch of non-empty dots. Abhishek, ask a question. This is being a bit greedy. I mean, well, it's not exactly greedy. Well, let's look at the tags. I mean, there is greedy. So, but essentially, it's not exactly greedy. There's a bit of constructive algorithm type thinking here, but yeah, I don't have the authority to block him, so I guess I'll leave it as it is, as we are coming to the end of the lecture anyway. Anyway, since we need non-empty buckets, that's what we're doing. Like every time we encounter an empty bucket, we're just keeping the bucket, and we need to print the bucket number for each I, right? This is just the output format which we need. Okay. Abhishek is asking if I'm going to do pura CP, like complete CP. I don't think I can ever do complete CP. CP is so vast that I can't complete all of it, and I don't aim to even get close to completing all of it because. But I would try to cover the basic things here. Yes, I would try to cover the basic things if that's what you mean. And I personally don't. Yeah. So Aniket is asking what exactly is constructive algorithms. So it's like constructive algorithms. You need to construct so usually the question asks you to construct a case which satisfies the following conditions instead of outputting an answer or something. Like, for example, in this case, you need to construct a coloring, like you need to construct a bucketing, like putting each number into a bucket. You need to construct that thing so that it satisfies a certain condition, and the condition is any two numbers in the bucket, any two elements in the bucket should have GCD AI AJ greater than 1. Yes, the final complexity is O of n. Correct, that's correct. So for example, in the previous problem, in the previous class, we saw that what is the problem again? Yeah, we need to construct three operations so that in the end it's 0. So constructing those three operations is the constructive part. making them 0 is the rule. And yeah, and final complexity is O of n for each case. That's correct. And yes, so there is that. Any more doubts? Abhishek, I do not know the answer for that, and I'm not in a position to answer as well. I'm just an educator who's teaching you. That's it. I don't know the answer. All right. Anyway, is this clear? Any doubts so far? Like, are there any more questions for me that you want to ask? Awesome. Aniket is asking if I will come up with tricky questions asked by interviews. See, I would if I could, but my company does not allow me to uh, like do anything related to interviews because there are some compliance issues such as conflict of interest and so on. Yeah, I would if I could, but I can't, so I shan't. Yeah. Abhishek, make a list for CP. I think there are plenty of lists out there, but I will try to come up with something. Once I get the time, I'll try to come up with something. All right. Any more questions do you have? You have for me? If you don't have any more questions, I can end the class. All right. Aniket, Abhishek, or Iran. Awesome. I hope you understood the class. I hope you understood the class, and I hope you learned something from the class. And I hope you've understood this problem clearly and the observations and the essence behind it. Like, yeah. So, all right then. I guess we can end the class now. After yeah. Abhishek is asking how I can approach DP. So first of all, DP, you can check my AtCoder series that I'm teaching right now. You can check my AtCoder series where I'm actually solving those problems, and I'm not only solving those problems, but I'm explaining a lot of concepts around it as well. For example, in the latest, you can check out my latest coins video where I actually talked about various concepts around probability, the various problems around coin toss probability as well, like around coin tosses, like a lot of variations. And then after doing all that, I came to the actual problem. So what I thought was not really necessary to solve the problem, but it was actually it gives you a lot of problem solving, a lot more tools for problem solving for coin problems in general. And I did the same for a lot of other problems as well. So I really want you to check it out if you. So there's no learning DP without solving problems. It's usually you learn it with solving problems. DP is one of those topics. Whereas like if in math you probably need to know the actual lemmas, or you need to like know how the proof works out and so on. But in DP you just get it with solving more problems. All right. Awesome. Is that clear? So you can follow my DP series, and simultaneously you need to solve problems on your own as well. Watching them will do you no help. I'm telling you now. And if anyone says that watching some series will help you, they're lying. All right. You need to practice them on your own. Yes, Aniket was right here. LeetCode, and then all 26 problems in Unacademy might be a bit hard. The last 5 to 6 problems might be a bit hard, but the first 20 problems, yep, you can check it out. And I'm going to take live classes on them. So on the next few problems, after I teach a set of problems, so it can be good to actually look at those problems and try to solve them on your own. And after that, you can come to my class and look at those videos. You can look and you can ask the questions live, ask your doubts live, so that I can answer them directly. I mean, there are plenty of Unacademy series on YouTube as well, but like if you come to the class directly, I can actually answer your doubts live. So, and teach this concept as well. So, yeah, awesome. Hiron, yeah, sure. Feel free to shoot one. Yeah, awesome then. I guess we can end this class. So if you found this class useful, please drop a like. Do drop a like, yeah. And if you think it's going to be useful to your friends, as I said, do share it with them. And don't forget to subscribe if you want more of this content in the future. Yep. Thank you. Okay, wait, just one thing. Abhishek asked any timetable. Usually I take it on Tuesdays and Thursdays at this time, because morning time is when I get the time. In the evening I have office, so that's that. Awesome. See you then in the next class, probably tomorrow. I think tomorrow is an exception, so I'm taking tomorrow day after I'm busy with something. All right, see you. Have a nice day.